it. Okay, we are live now, I can see.
Great. Welcome anybody tuning in. We'll get started in just a minute or two. Thank you for joining us today. I think someone is having some background noise, so if the other participants could mute their. All right, it's now noon, so let's go ahead and get started. Hello and welcome to the Quake briefing on the Tonga volcanic eruption and tsunami of January 15th, 2022. My name is Elizabeth Angel. I'm a communications and program manager here at EERI, and I'll just be taking a brief moment to introduce us before I hand it over to the leaders of the Northern California regional chapter, who will talk about today's event and our speakers. Just a brief word, if you're not familiar with EERI already, we're the leading nonprofit membership organization connecting multidisciplinary professionals who are working to advance earthquake resilience both in the US and globally. And by joining us, you become part of a community of practitioners, researchers, and students from a wide range of disciplines who are working together to learn more about earthquake risk and reduce it around the world. I'll hand it over now to Volkan Sevilgen, who's the president of EERI's Northern California chapter, to talk about the chapter, which is hosting today's session, and introduce our speakers. Thank you.
Hi, everyone. My name is Volkan Sevilgen. I'm the president of the Northern California chapter of Earthquake Engineering Research Institute. We are dedicated to reducing earthquake risk in Northern California. And the best way of doing this is to learn from everybody else's experiences. And this is one of those events that we are learning from everybody else and focus on Northern California. Today, we are going to talk about Tonga earthquake, not the earthquake, the volcanic eruption and tsunami following. And I'll be directing questions to the speakers. We have excellent speakers today. And if you put the questions on the YouTube comment section, and I will direct that to the speakers. So to introduce our great speakers, Bruce Mason, who is also our chapter's secretary and treasurer. Thank you.
Thank you, Volkan. I would like to welcome everybody to the Tonga eruption and tsunami briefing. My name is Bruce Mason. I'm a secretary in the Northern California chapter, and I'll be serving as a moderator today. The intent of the Quake briefings is to be something available for free to everyone. So people that are members of EERI get the announcements. But if you're currently not a member but want to get announcements, please send an email to me at that address. We'll put you on the mailing list. But what we would like is for you to consider joining EERI. It's a wonderful organization, and we would welcome any new members. Next slide, please. Last month, on January 15th, a violent eruption occurred within the island nation of Tonga in the Southern Pacific. This was the most violent eruption in about 30 years. The energy release was estimated to be equivalent to a magnitude 5.8 earthquake. The eruption obliterated an island and it caused a tsunami. The tsunami had great effects in the immediate vicinity. It destroyed or caused much damage in the capital island of Tonga, but the tsunami waves affected the entire Pacific Rim. Our briefing today features two speakers. The first will address the eruption mechanism, and the second will explain how the tsunami affected California. Here's our format for today. Each of the speakers will talk for about 20 minutes each, and the remainder of the time will be devoted to question and answer period. So our total program today is about 60 minutes. Now we encourage questions from the audience, and how you will do that, as Vulcan mentioned, you will add a comment that's at the bottom of your YouTube screen, and then behind the scenes, Vulcan will take these questions and come back later in our program and pose the questions to our speakers. Now, we recognize we might have more questions than time allows. So each of the speakers today have kindly provided their email addresses, and you see them here, and they will try to answer your questions over the coming days. You can send them questions directly, and in the future, they'll try to answer your questions. Now, what I would like to do is introduce our first speaker. Jacob Lowenstein is a research geologist with the U.S. Geological Survey and chief of the Volcano Disaster Assistance Program. He will be giving us an overview with regard to the eruption mechanism. Jacob, could you please proceed?
Sure, I assume you can hear me. I'm going to now share the screen. Okay, all look okay?
Yes. Looks
All right.
good.
Well, today I'm going to talk about what we know about the eruption of the Tonga Ha'apai volcano, which the eruption occurred at 0400 UTC on the 15th. I'll discuss its regional context and interesting volcanological aspects. I've never personally worked in Tonga, but I have followed the events pretty closely with my work with the Volcano Disaster Assistance Program, which is the international arm of the USGS Volcano Program. It's largely funded by USAID. I've talked with lots of people, both in the US and in New Zealand, as well as Tonga over the past month, and information I'm going to present is drawn from a lot of people who are shown in the slide, and from the existing literature as well. I'll specifically point out that most of our geological knowledge about Tonga Ha'apai comes from Shane Cronin, a professor in Auckland who has worked on South Pacific volcanoes for many years. Let's see. The eruption was really remarkable in that it created a tsunami, which is of primary interest to this audience, but it was also an incredibly forceful eruption with a plume that entered the mesosphere, which is unprecedented. It had the loudest explosions for a volcanic eruption since 1883's Krakatau. It had record-breaking lightning. There were gravity waves in the atmosphere, and it generated debris flows that apparently traveled on the order of 20 kilometers to break the fiber optic cable that supplied most of Tonga's internet access. Even so, in terms of the amount of magma erupted, it doesn't appear at this point that the eruption was as large in terms of magma volume as the 1991 Pinatubo event. So it's interesting, confounding. It might not be totally unprecedented, however, as it seems that witnesses have seen similar things at Tofua, 100 kilometers north of Tonga, and may have been left with an impression not dissimilar from what we just saw. 3 Samoan deities conspired to steal Tofua, so they came and tore up the high mountain by its very roots, and its place was taken by a large lake. This enraged the Tongan gods very much, and one of them, Tafakula, essayed to stop the thieves. He stood on the island of Luahako and bent over so as to show his anus. It shone so brilliantly that the Samoan deities were struck with fear, thinking that the sun was rising and that their dastardly work was about to be revealed. Hence, they dropped the mountain and fled to Samoa. The mountain became the island of Kau. So this shows that islands disappear and they grow in very short periods of time in Tonga. Here's a little bit about the regional setting. We've got an intra-oceanic subduction zone with the fastest convergent rate on Earth, around 23, 24 centimeters of old, cold oceanic crust. Here's the Tofua Arc. It goes back down into the Kermadec and New Zealand further down. Vanuatu is another arc over here. The Fiji platform is complicated in the back arc, and then we have a hot spot over here in the Samoan Islands. And here's a cross-section of the area showing the uplifted volcanics and limestone platform. The arc sits behind it where the volcanoes are, and then there's the Lau Basin behind that that's an active spreading center. So the limestone islands and platform is in here. This is Tongatapu, where the capital Nuku'alofa is. And then the volcanoes, both active and slightly less active, are all back here. There's a lot of them. Hunga Tonga, Hunga Apai is right here, and it's about 70 kilometers north of Tongatapu. Here you can see the islands. Subaerial islands of the volcano were tiny and uninhabited right in here. But as you can see on the right, they're really part of a much larger volcano. It rises about 5,000 feet above the ocean floor. It's a caldera that's 4 or 5 kilometers across. It's caused by evacuation of large amounts of magma during massive eruptions in the geologic past. And the volcano islands that we see are really just on the crater rim or the caldera rim. That in 2015, the volcano was active and it filled in the area between the two islands. And then you can see that the caldera extends here. Most of the water level is in the middle is around 200 or meters, but things shallow out in this region right here. And Shane Cronin's work has shown that there was a large eruption, perhaps of VEI 6. We'll talk about VEI in a minute. That happened about 1,000 years ago. Most of the more recent eruptions, including several in the 20th century, were smaller. Some quick definitions. Circean is often applied to eruptions that come from mafic or basaltic andesite volcanoes in water. It's characterized by steam explosions that eject lava fountain fragments as pyroclastic surges. You'll also hear the term phreatomagmatic, and hydrovolcanic, which both imply reaction of magma or interaction of magma with water. But bigger eruptions are known as Plinian eruptions. These are the ones that go up into the stratosphere and have global impacts. They create a lot of pumice normally. And then there is also a possibility you can get sort of runaway Circean events. That would be what just happened in Tonga. That might be called a Phreato-Plinian event.
Plinian.
Then we have the volcano explosivity index. And that is shown right here. And essentially we try and put labels, sort of magnitudes for the size of different eruptions. And it's based on the amount of material that's erupted. And so, for example, Mount St. Helens was around a VEI 5 with a less than actually about a cubic kilometer of magma erupted. Pinatubo in 91 was about 10 times larger. So it's around a VEI 6, Tambora, VEI 7, etc. So that's how they're defined, but it implies that you can actually measure the amount of magma erupted. And that's not always that easy, especially here. The magma type erupted at Hunga Tonga was dominantly basaltic andesite and andesite. It's important to point out that substantial dacite, more silicic magma has been created in the Tofua Arc as well. And so you can get fairly explosive eruptions in this area. It's thought that that happens because you have relatively shallow magma chambers where crystallization is occurring and magma differentiation is occurring. And that allows you to create the more silicic materials. But even the more mafic materials, the basalts, basaltic andesites, are believed to have relatively high dissolved volatiles like water. And so it's very possible that that makes it more explosive, that there's more volatiles in these magmas than in some, and therefore you have the potential to start out fairly explosive. Okay, so it's important to note that there was no monitoring prior to this December, and I think there's several reasons for that. First, Tonga is a small country. It doesn't have that many people. It certainly doesn't have a lot of PhDs in geophysics to run monitoring systems. As we've seen, the Tonga volcanoes are generally located away from the population centers, and deaths due to volcanic eruptions had not occurred in historic times. There also had been attempts to install seismic networks locally, but eventually the equipment fails. There's nobody there to pay to replace them, and there's nobody there to fix them. And so largely these have not been successful. The volcano started erupting in late December with phreatomagmatic activity that was pretty substantial. The Tonga Geological Services was active in messaging to the Tongan people and provided useful advice given the scale of the observed activity. Without active monitoring, it was not easy to know what would happen next, especially after eruptions ceased in early January. And here's an eruption from the first eruption on January 14th, early in the day, late in the day on the 15th, but 0400 UTC. Okay, now we're going to put together some images of the weather satellite data of the eruption. These images are collected every 10 minutes. They actually take 10 minutes to collect. And so this area in here, in this case, was seen at around 356 UTC. The slides were put together by my colleague, Alexa Van Eaton. Tonga Tapu is at the bottom of the circle here. The volcano is in the center. And then when we move to the next slide, you can see, I can move back and forth here. There's a little plume that's visible by 406. And volcanic lightning starts at 408. At 416, 10 minutes later, the plume's already 16 to 18 kilometers high. The NEIC calculated that the explosion, which is translated into an earthquake, was a magnitude 5.8, and that had already happened around 4:15. So around 10 minutes into the eruption when that happened. Here we are at 4:26. The umbrella is reaching Tonga Tapu, and this is when we're starting to get a lot of booms. That are arriving. Most of them are happening in this time period, about 4:25 to 4:45. Now, this is the central overshoot where the temperatures are actually starting to warm. The material is getting up into the mesosphere, 58 kilometers. So this is 150, 160,000 feet compared to where the stratosphere starts at 50,000 feet. So this is getting really high, extremely powerful eruption. Here you can see most of the material in the stratosphere. It's at 446. Another final expansion. And then after around an hour, the upwind expansion slows down. Models for plume growth with time, as shown in this plot, imply that mass eruption rates are among the highest ever seen. So this is the minutes after inferred start. This is the radius of the umbrella cloud. This is the Pinatubo eruption, and you can see that this eruption, the plume was growing very quickly. Again, very explosive and a lot of material being erupted very rapidly. Here's an image of the subaerial part of the volcano as it looked in early December. Here's the material that was growing in 2015. On the 14th, this all disappeared during that first eruption. And then by the end of the eruption on the 15th, all that was left is this tiny piece here and this tiny piece here. So tremendous damage done by this explosive eruption. Here are the lightning data plotted and provided by Alexa. There were around almost 400,000 strikes, or about 4 times the previous record holder, which was Anak Krakatau a couple of years ago. There are two main pulses of activity, magma extrusion essentially. As we'll see, this is also similar to what we see in the seismic data. Lightning is promoted by fragmentation of magma into tiny particles, as would occur in a phreatomagmatic eruption. It's also promoted by the formation of ice, which is enhanced by seawater entrainment. And the ascent of the plume into the upper troposphere, where the temperatures are frigid, and so any water that's sent up there immediately turns into ice. Okay, a little bit of seismic data. First, look on the right side of the screen. This is the seismogram recorded at the closest seismometer in Fiji, 750 kilometers away. As you can see, there's intense seismic energy starting around 400 UTC and finishing around 5 hours later. As with the lightning data, you can see two major pulses. This must have been a very noisy eruption to be able to record at 750 kilometers away. And of course, there was also the tremendous explosions you've read about. And those we can infer a little bit more about from this data from Fred Pollitt to the USGS. He plotted up the vertical force vertical force that gets transferred to the ground, sort of if you had an upside down rocket. Each of those is providing an impulse that you can measure with regional waveforms, or you can try and assume the vertical force, which is huge for each of these. They're happening in pulses over around the first 2,000 or so, 1,500 seconds. So that's the first 25 minutes of the eruption, where you're getting these really forceful explosions, and that's mimicked then by the infrasound data and the sound waves that people are seeing. Yeah, I think that's about it. So these explosions are happening 25 minutes, but the eruption itself is lasting hours. Here are the ripples in the stratosphere as seen by the infrared imaging with NASA's Aqua satellite. The initial wave or waves in the atmosphere are thought to be Lamb waves that traveled at or higher than the speed of sound. And they're thought to be responsible for converting their energy back into the ocean to generate tsunami waves that reach distant shores faster than would be expected for typical earthquake-triggered tsunami waves. Here's the volcanic cloud as seen on the 17th from a polar orbiting Calliope satellite. It's LiDAR data, and you're seeing that this is, again, it's polar orbiting, so you have the pole out in this direction and out in this direction. Here you've got the area where you can see the plume at 30 kilometers or 100,000 feet or so. That's where the main volcanic cloud stuck after the eruption. Again, this is on the 17th. And then the LiDAR can't get through, so you really don't see anything happening below it. Now, though that plume contained a healthy amount of volcanic sulfur dioxide, it wasn't as much as we'd normally expect for a VEI-6 eruption, something around the Pinatubo size. On the other hand, it does appear to have generated, in this case, the numbers shown here at 415,000 tons of sulfur dioxide, compared to about 20 million or something for Pinatubo. It does appear, though, that there was a huge aerosol cloud composed of sulfate, as seen by other satellites. And so right now, one of the things that people are trying to figure out is whether the SO2 could have been rapidly converted to sulfate, or whether some of the SO2 was removed by ocean water. And anyway, these are topics are things people are trying to understand, as well as many other things that happened during this fascinating eruption. All right, so why was this so explosive? Well, you have interaction of magma with ocean water. So we've talked about that, phreatoplinian, phreatomagmatic. Clearly, there was very efficient mixing and fragmentation to transfer the heat from the magma into the water that was rapidly boiled and sent up with magma into the atmosphere. I think water depth is probably quite important here. If you were 1,000 or 2,000, if you were thousands of meters below the surface, you would quench the eruption, or at least it would have minimal impact. If it's too shallow, it'll be a fairly normal eruption. So you're basically decompressing something from 10 or 20 or 30 bars, and that's happening very rapidly, and you have a huge pressure change, and that causes huge sound. It's also possible that this was magma was already volatile rich, and so that contributed to pushing it out fast and then hitting that ocean water. And then it is possible that the tsunami and the explosivity were related in some ways to magmatic or geological processes beyond the atmospheric effects. For example, is it possible that the caldera collapsed several meters or even tens of meters, and that allowed a huge amount of water to fill in that void and then start the waves? Or the landslides, ruptures of geothermal seals. These are all things that people are considering, and we'll have to see what we find out in subsequent months and years as this eruption is studied further. Okay, a little bit about the earthquakes. Even though there weren't nearby seismometers, there were earthquakes happening, and we know that now in retrospect because they became very noticeable after January 15th, and the NEIC got interested and started working hard to look at the data and tease them out of these distant seismograms. So the map on the right, this was taken just a few days ago, so you see that all of these are post-eruption. The yellow one, the white ones are more recent. But all of these are happening. They're poorly located. They certainly would and do represent something closer to the volcano, but here's Tonga Tapu down here. They're all greater than about magnitude 4.5 because you can't locate anything smaller than that with such distant seismometers. And they're smaller than 5.1. So between 4.5 and 5.1, they're fairly large earthquakes. On the left, you can see a timeline, and Will Yeck from the NEIC has helped put that together. You can see lots and lots of individual events happening in the days after the eruption, starting up really a couple of days after the eruption, and now they're slowing down. You can also see that there were earthquakes prior to the 13th, 14th, and 15th. And so presumably there would have been a whole lot more small activity as well, magnitude 2s and 3s and 1s and things like that, that could have been seen had there been more equipment. Okay, what about that undersea cable? It was about 20 kilometers south of the volcano, headed from Nuku'alofa out to Fiji, to Suva. The folks from Kentic.com reported that internet traffic dropped off around 0430 UTC, which is around when the tsunami hit Tonga Tapu, so it's possibly indicating when power was lost. An hour later, all traffic dropped, and you can see that in this plot right here. And it seems to be that was when the underwater debris flow or some sort of debris flow snapped the cable in at least 2 pieces and moving it at 5 kilometers from its original position, at least. Okay, so in summary, we have a really explosive eruption, but the magma volume ultimately is unknown. There's very few places to collect ash, and so it's hard to put together isopachs. We don't know how much erupted underwater. We'll find these things out, hopefully, soon. The tsunami seemingly was related mostly to the atmospheric disturbances, but there are geological activities that could contribute to some of the waves and some of the motion of the water due to this huge event. And that's all I have for now. So we'll let Bruce talk, and we can answer questions later.
Okay, Jake, I really appreciate your presentation today. It was outstanding. It was the right level of detail for our audience today. I know I learned a lot about volcanoes from your talk today. One of the more interesting things I learned is volcanoes sound more interesting than earthquakes. That's a little light humor. Okay, what I would like to do now is proceed to our next speaker today, and he will be addressing tsunami impacts in coastal California. I would like to introduce Rick Wilson. He's the Tsunami Unit Manager of the California Geological Survey. He will present on how the tsunami affected California. Rick, please proceed.
Okay, thank you, Bruce. Can you see my screen okay?
Yes, make it full screen though.
There we go.
Looks good.
All right, thanks for the introduction and Jake's great presentation. I think I agree, volcanoes are really interesting. I'm hoping I can convince you also that tsunamis are interesting from the standpoint of how it affected California especially. So I'm going to focus on the tsunami advisory for California from the Tonga Ha'apai, which I'm just going to refer to as the Tonga volcanic eruption from this point forward, or I might refer to it as the 2022 tsunami, just to simplify that. I'm going to talk about the sources that are being investigated right now and how they influence the tsunami generation, especially the trans-Pacific generation of tsunami. I'm going to go through a timeline of what we were doing in California from a response perspective, understanding that this was a very complicated event for not only the National Tsunami Warning Center, but also other experts, at our level that were dealing with this particular interesting and complicated event. I'm going to talk about the impacts that we saw in California and also some of the lessons learned. We have a lot of different partners we work with, but I wanted to highlight the partners down with their logos below, and hoping that you can visit our website. We have a Tonga page for this particular event, and I'll provide that at the end of the talk also. So I'm going to stop this movie right here, but as I said, this was a very complicated event. I am not as much of an expert on how we can kind of unwrap what the sources were from the tsunami waves, but that's what I rely on our colleague Patrick Lynette from USC and his colleagues who are working on this very question. And what so far they've come up with, I think as Jake mentioned, there's a lot to learn and it's going to probably change over the next couple of years, but thus far they have seen a precursory source that was about 10 minutes prior to the major eruption. It may have been related to a landslide or a smaller eruption prior to the main eruption. There was also an explosive eruption which caused a shock wave of high pressure. But the idea is that this is probably not what was responsible for the significant tsunami in the far field, but may have generated some significant waves locally. There was also, as Jake mentioned, potential for the crater to collapse or the caldera to collapse, which had possibility of creating a large amplitude, but a very short period tsunami, which may have affected the local region. But as Jake also mentioned, it appears that the acoustic high air pressure pulse that was generated seems to be the primary source for the tsunami. And what you see here in this movie is the red is the actual pressure wave going across the ocean. It's leading out across, from Tonga. It went across the Tonga Trench, which in talking to Pat, it seems that is what actually caused the larger tsunami. When it goes over deep water, it generates a larger amplitude tsunami at that point. And it appears that going over the trench may have generated this, the larger wave that we saw, and what would normally the travel time that we saw from this area. But the red is the pulse, and I'll just let the movie go so you can see that pulse going across the Pacific. It hit Hawaii and then hit California. And as it came to California, that pulse also carried some tsunami with it, tsunami waves. They were smaller waves, and I'll show a barogram, a tide gauge reading of that. But you can see the bigger pulse is actually following it, the bigger waves. The interesting aspect of this too is that the pulse actually traveled across land and created a tsunami in the Caribbean and in other locations. So this was a very unique event that we're going to learn a lot from. And so a lot of uncertainty as to how the whole thing came together, but it appears that acoustic air pressure pulse going across the Tonga Trench is really what generated the larger tsunami for California and the West Coast. This is a timeline of our activities during the tsunami, and it really shows kind of the response from a federal, state, and local levels. The event happened about our time in California at about 8:15 p.m. Pacific time. There was a lot of uncertainty whether this actually could cause a large tsunami in the far range, but once it hit Hawaii, the National Tsunami Warning Center started taking notice and put out a message saying they're analyzing the event to determine the level of danger for California at about 3:30. And then about 3:45, our agency, as well as Cal OES duty officer, met and started to ramp up our actions. And that included sending out a message to our tsunami event distribution list, which is comprised of emergency managers and harbor officials. At 4:30, we had a call with the National Tsunami Warning Center. The first part of the pressure wave they mentioned did show something, but it was relatively small and non-threatening, but the larger pulse was following it, and it would arrive along our coast about 7:30. They also were telling us that it is likely, because of what they saw in Hawaii, that they would like to put us into an advisory level alert status. And so this really ramped up our activities. Advisories are basically 0.3 to 1 meter in height. That doesn't seem like a lot, but it does a lot of damage potentially to harbors. And if you combine that with high tides, you could see some flooding along beaches and within harbors. So we advise people, the locals, to keep people away from the waterfronts and off beaches. And many of them move forward with that response. First arrival was 7:30 to about 8 a.m. in the morning. Of course, this was a 3-day weekend for many people. It ended up being kind of a long day for some of us. Because the tsunami advisory actually lasted for about 19 and a half hours in California, as the way that they call off the advisory or downgrade the advisory is it has to have the tsunami has to show that it is below the threshold of 0.3 meters for 3 hours period of time on tide gauges in the region. And it took a long time for that to happen. So it was a long day, but we got through it. Then we also had post-tsunami activities where we sent people into the field and also collected information on surveys. And I'm going to talk about that. That forms the basis for a lot of my presentation. The tide gauge reading on the right there kind of shows that first pressure wave occurring or arriving at about 4:30 in the morning, and then about 7:30 to 8 o'clock, that primary tsunami started. So you can see there kind of the difference between the first pulse from the pressure wave and then the primary tsunami that was likely caused by that atmospheric pressure wave too. So before I start talking about what happened in 2022, I want to really kind of go back to 2011 and show what was happening in a place like Santa Cruz Harbor and compare that to what happened during this event. This particular tsunami in 2011, that was the Tohoku Oki earthquake in Japan, was the cause. Caused a lot of damage to harbors, about $100 million in our state, but it did not inundate dry land because it basically occurred at low tide conditions. So most of the tsunami, if not all the tsunami, basically was contained within the tidal range. And so it was kind of a different character in this case because it did not occur at the same time as the high tide, as we saw in 2011. So we saw a lot of damage in harbors, but no flooding. In 2022, last month, we saw quite a bit of flooding along beaches and also in some harbors. And these are pictures from Santa Cruz Harbor and Santa Cruz Beach and Boardwalk, and you can see the flooding on the beach as well as the flooding within the harbor. And this caused a lot of damage in this particular area, on the order of about $6.5 million worth of damage compared to about 25 million in 2011. But because of the amount of water kind of entering in, leaving the harbor was less from the tsunami, that's why we didn't see stronger currents in Santa Cruz in 2020 in this last event. But because it was coincident with high tides, we saw this flooding around the harbor. So it's kind of doesn't make as much sense when you look at an advisory, a smaller tsunami flooding more land, and a warning level event that doesn't flood land. So it really ties to the tides and the tidal range. So next I'm going to go through some locations in California and what the impacts were, and then other locations where we didn't see any impacts. I'm going to start with one of those locations we would expect to see impacts. Crescent City, we basically have had a team up there and talked to the harbor master. After 2011, the whole inner boat basin here was destroyed and rebuilt. After that, it took about 5 to 6 years to rebuild it. And they increased the size of everything. They supersized it, if you will. They went from 10-inch piles to 30-inch piles to make sure that they were more stable for smaller tsunamis. They also built I don't know if you can see my cursor, but they built a dock near the entrance that actually was a deflector dock that dissipated the tsunami, and especially the tsunami in 2000, this recent one. So we had no damage reported here, but it does kind of show that you can develop and improve harbors, and those improvements can save you money from smaller tsunamis in the long run. This is a video from Berkeley. So we're a little further down the coast inside the bay. And this was a video taken by one of our geologists in the program, Jackie Bott. And she went out she lives in Berkeley, and so she went out to the harbor and took this video of the currents going in and out of the harbor. Although it doesn't look like it's very significant, the currents were difficult for some vessels to navigate, and it actually caused one larger sailboat to make 3 attempts at docking in this area. The harbor officials did a good job getting people off the docks and out of the boats, although we didn't expect it to go onto dry land here because there is some protection within the bay, even with the tides being higher. But they made sure to evacuate people that were living aboard the ships, the vessels. And this is something we're seeing more of, a lot more people that are liveaboards on boats to save money. So that's something that harbor masters are tasked to do before tsunamis like this arrive. On the west side of the bay, north of the Golden Gate, there was damage to several docks and boats near the community of Mill Valley. And although this area appears to be protected from the outer coast and what you would think would be significant tsunami buildup, the tsunami entered into Richardson's Bay, which is the big bay north of the Golden Gate there. And it funneled into this narrow waterway in the back part of Richardson Bay. That funneling effect not only added to amplification of the tsunami with the higher tide, and we saw some flooding in and around this area, but it also, as it suddenly changed directions in and out of this U-shaped harbor at the back of the bay, it caused some very strong currents that dislodged docks and damaged boats. So this was one of those situations where it's just not a prime location necessarily for this type of tsunami activity, and could, amplify the effects because of the way that the area is developed and built there. A little bit further down the coast in Monterey County, we observed some additional impacts. In Moss Landing, a number of piles and docks sustained damage, as shown in the picture on the left. In Monterey, the high water levels around that occurred within and near the pier and the waterfront area almost flooded businesses on the wharf that you can see there. The blue line that's going across, that's kind of how far the water got up, and you can see some of the businesses were just above that. So very close to having flooding to some of these businesses on the wharf itself. Further south in San Luis Obispo County, we saw additional impacts from flooding. And the photo on the left shows flooding at Port San Luis. This is also one of those hotspot locations in California where we see amplification of tsunami waves offshore at their tide gauge, but we also see that it has the potential for increasing the size of flooding in this area. So this is the harbor headquarters structure, and part of it got flooded during the tsunami. The area of Oceano Dunes, and it's a recreational vehicle area. That's the photo on the right, shows that the sudden flooding occurred and it stranded some people who were camping and had recreational vehicles out in this area. So this was something that caught some people off guard that were camping in the area. Then further south, kind of the area that got the second worst damage from this event was Ventura Harbor. We saw damage to over 20 docks and actually had one of their harbor patrol boats capsized. The harbor has a unique shape, which likely caused more problems. The map on the left shows areas of, this is a modeled result from 2010 tsunami from Chile. So it's a tsunami coming in from the south at an advisory level tsunami, similar to this one. It shows damaging currents going into kind of the main entrance there, but water will rise in the back part of the bay where those narrow areas are. Those are called the keys. And in that area of the keys, the water fluctuation is really what causes damage to docks. It dislodges the ramps to the docks from the main docks, and the docks are free floating at that point and dislodged from their piers. And then as that water comes out of those key areas, it funnels through a very narrow area where their patrol dock is. And that's what caused the strong currents that took this one boat under and capsized it. So they lost that particular boat from this event and had some other damage to other docks too. So overall, we saw damage on the order of about 8 to 10 million statewide. Santa Cruz reported the greatest amount of damage, probably 6.5 million because of the flooding and also some of the docks being damaged by some strong currents within the harbor. The infrastructure that got flooded and some of the buildings, and they also have a sediment barge that they have that was also damaged. Ventura Harbor, 1 to 2 million, docks and boats both. And then we saw, damage to other areas, probably a half dozen areas along the coast that added up to several $100,000. Really, the response actions and our after actions are here. We need to improve our timing on the content of early information going to the local officials. Every hour they get information and have a plan in place, the people are better protected, and we have to do a better job with that. We only gave them about 3 hours in this case. This event also drove home that the advisory level alert is really one to pay attention of evacuating boats or evacuating beaches and harbors, especially the people in and around them. And we need to improve our outreach and preparedness to the liveaboards that are on these vessels in the harbors. And that this event really demonstrated how some of our decision support tools could have been used. We have a support tool called Playbooks, which not only identify strong currents within harbors, but for certain events, once we get the forecast information from the warning center, but we also can show where the potential for flooding can occur. And we did some post-event analysis and found that if we would have been able to get the tsunami amplitude prior to the event, that we would have been able to show that this particular area could have flooded, and we would have predicted that ahead of time and provided that information to the harbor. And so our harbors and our cities have these maps, and it really shows areas where potential flooding can occur. And it's part of our process we normally do, but given the time and the complexity of this event, it really didn't come to fruition in this particular case. So we just need to probably do a better job on the timing part of it if we can. So that's my presentation. And if you do have questions that you can't get answered here, please email me, or you could look at our Tonga website, and we'll be probably putting out a report over the next month. So thanks.
Hey, Rick, thank you for an outstanding presentation. I really enjoyed the pictures of the damage. Here was the event was 5,000 miles away and was able to cause damage on coastal California. And it rather surprising for me. Okay, that ends my part of today's presentation. What I'd like to do is turn control of the meeting over to Volcan to be able to start with the question and answer period. Volcan, please proceed.
Thank you, Bruce. Well, it was an amazing two presentations, and one was very explaining how volcanoes are working, and the other one was how tsunami impacted California. I didn't realize that there was this much damage in Californian coast, so this was a eye-opener for me. My question is, and I encourage everyone to post their questions on YouTube as I am asking those. So one question that I have is, Rick, you mentioned that this event caused more of a flooding type of tsunami impact in our harbors compared to 2011 Tohoku earthquake tsunami, which was more like a high-speed impact. Why do you think that's the case?
It's primarily driven by the tides in this case. I think that's when we add a tsunami that's about a meter and a half to a high tide, it has more of a flood potential than a 2 to 3 meter tsunami that's at low tide. So that's part of it. I think also with less water in some of the harbors, you strengthen the currents. Yeah. And when you have harbors flooding with more water and then flooding out, ebbing and flowing, that's what causes these strong currents. So I think that's why we saw the stronger currents in 2011, was the water column was basically forcing the water in and out. I should also mention that this was the first tsunami where we actually had flooding of land since 1964 in California. So it's been a while since we've seen that.
That's incredible. And that's a very, very important insight that you are giving. So anyone who is doing, tsunami hazard models, they should also take into account of the tide. Correct. Because that really changes the whole picture and what would be the impact. So that's very good. Bruce, do you have any questions? While I'm waiting for people to come in from YouTube.
Of course. I have many questions. It was a very interesting talk. This one's for Jake. You mentioned about the acoustic effect causing the tsunami. What speed does that acoustic wave? Is that the speed of sound? In other words, when it's propagating over the ocean, is that the speed that that the tsunami is being moved at? I guess. Go ahead.
Yeah, some of these sound waves are moving at the speed of sound, and my understanding is that the LAM waves can move faster than the speed of sound. Even they can be very, very, very fast. So I don't know a whole lot more than that.
Okay, very good. Okay, a question I have for Rick has to do with the San Francisco Bay Area, where many of us live. One thing that always amazes me, it seems the Golden Gate is only about 2 miles wide. So if we have a wave coming in, it just seems intuitively that it would dissipate once it gets into the bay because we have such a big opening. Is it a hazard because of this funneling effect that you mentioned? Could you elaborate on that?
Yeah, you're right, Bruce. So we do get some dissipation as it enters into the bay. If most of the modeling we've seen, so like our worst case scenarios, we could see tsunamis that are 20 to 30 feet on the outer coast. And once they get inside the bay, they go down to about 10 to 15 feet. So you lose quite a bit of water in that respect. However, when they do go through narrow openings and get funneled, they pick up not only speed, but they also pick up the potential for amplification. So it just depends on the setting that the water is going in and out of. And like that one I showed in Mill Valley, that's one of those locations that was kind of a more hazardous area because of the setup.
Okay. Well, another question I have for Rick is the idea, how many cities actually had evacuations? Or can you put some magnitude on that? Was that, did a lot of people evacuate? Because to be quite frank, I really wasn't aware of this living in the San Francisco Bay Area.
Well, we knew this event wouldn't be one of those where we needed to like do our worst case evacuation. And that's what a lot of communities have, is the maps that show what a worst case would be if they had no other information. They should get out of those areas. We knew this would be more of a beach event and a harbor event. So they knew that an advisory level, and because of the high tides, we really put out the message that treat this like a king tide condition.
Oh.
And so people can kind of relate to that they might expect some flooding of the beaches. And so they closed the beaches, which was great. There were still people that were stranded that had to be rescued in certain situations. We always get surfers that want to try to surf the tsunami. Yeah, closing the beaches, getting people off of boats, getting people off of docks, that was the priority. And most cities and most harbors did that.
Okay, excellent. A question
I
for
have
Jake.
a question before.
Go ahead.
So, Rick, also you mentioned that if you knew the amplitude of the tsunami, you would be able to inform the harbors about the potential flooding. Who is responsible of providing that information, and what else can we do for the future events so we don't have to face with these impacts anymore?
Yeah, that's a good question. So we work very closely with the National Tsunami Warning Center. They're the ones that provide the tsunami amplitudes prior. It's kind of their forecast of not only when the tsunami is going to arrive, but also what the amplitude should be. Unfortunately, this event kind of threw them for a loop because their setup, their forecasts are based on earthquakes. And they're not based on volcanic eruptions. So they couldn't come out with those forecasts very readily. But we do have a tool in place in California for distance source tsunamis, where if we know what the forecast is, we can put it into our program, computer program. It tells us what the total water level will be in an area, and we can match that against these maps we've already distributed to the cities and counties. So we have that plan in place. They're called the playbook approach. It's basically like a sports analogy that we're defending against a tsunami that's on the offensive. But we work with cities and counties to do this. And in this case, we weren't able to do it ahead of time, but evaluating it afterwards, we could have seen that we could have predicted that if we would have known the amplitude information.
Thank you. And I have a question for Jake. You mentioned that this the eruption might have some precursors and seismicity precursors. And I think that's more or less common for volcanic eruptions to have some kind of seismicity precursors. My question is, how often do you see precursors, and how often do you see a lot of seismicity without eruption?
Yeah, well, this is, you get both. So it's not that common to see earthquakes this large. I mean, the fact that we can go back and see that there were earthquakes over magnitude 4.5 happening before the eruption, and we haven't gone back further to know, but is somewhat unusual. Oftentimes we might have 3s and 2s even that will be sufficient to help forecast eruptions. It also depends how frequently a volcano has been active and whether the rocks underneath the volcano are already broken or whether they need to be broken in order for the magma to move towards the surface. So that was part of your question. There was another part too.
How often do you see precursor look like earthquakes with no eruption?
Yeah, that happens too. I mean, even in the Western US, you get all these swarms in volcanically active areas. In some places where you don't really know whether it's a volcanic possibility or whether this is just purely a tectonic swarm. So these things can happen. And as volcanologists, we're normally looking at how close is it to the volcano, and do we see any other activity at the volcano that we could interpret as showing that it's getting active. And so that often involves satellite data, thermal data, geodetic data to see if there's deformation that's related to the volcano.
You also mentioned that there was a quite sizable earthquake, perhaps just before the eruption. So do you think perhaps that earthquake might have triggered the eruption?
I guess for the most part, I would interpret it that the magma has was on the move, and it was
Okay.
generating earthquakes by breaking rock. And it's just a question of how, if we had had a good network in that area, what would we have known? How soon would we have known? But in general, I think that, in volcanoes, it's a little tricky, but often the volcano is pushing the earthquakes and not the other way around.
Okay, so that's a very interesting point. Bruce?
Okay, we have time
We have
for
2 more minutes.
Okay, perhaps one more question. And this would be directed towards Jake, just for my understanding. You talked about the mechanism of the explosion. My understanding prior to your lecture today was that the idea that when the water gets down onto the hot magma, we have this steam, this large volume, and that's what causes the explosion. But I think on one of your slides, you mentioned like a landslide or part of the caldera breaking away. There were some other mechanisms there. Could you just briefly mention, and which would have been the primary thing that would have caused the explosion, please?
Well, in the end, it appears that maybe a cubic kilometer of magma, maybe even more, maybe a little bit less, got out. That's a huge amount of material, right? It's a kilometer by a kilometer by a kilometer. That's all magma that got out in the space of 3 hours, 4 hours, and most of it early on. So something happened to rapidly introduce a lot of material into the area where there was ocean water, and there was a reaction between those, generating big explosions as the water expanded and as the magma expanded as pressure was decreased. So yes, so what made that happen? Well, one possibility is that some sort of a landslide happened as a result of deep stabilization of the edifice, and that depressurizes the system, uncorks it, and allows depressurization to occur. And then I understand that there's some data showing that there's some geothermally altered materials that were present as tiny lithics in the ash, implying that maybe there was a fairly impermeable cap on the system that broke, maybe, for part of the magma that was contained. So you again have to understand this is a really big area. Maybe only a small area was erupting on in December, and a little bit more opened up on January 14th. And then something happened on January 15th that allowed more magma to interact and cause more explosivity.
Okay, thank you. I think we're drawing near the end. I would like to thank both of the speakers, and then Vulcan to make
Bruce,
his remarks, please.
I'll ask a couple more questions, because I'll just use the liberty for going over another couple minutes. One important question is, you mentioned that since there were no one in Tonga to be able to monitor seismic stations, there's, in a sense, the opportunity has been lost to use this case as a good research data. What can we do? How can we avoid that's happening in the future? Because I'm assuming good eruptions are like good earthquakes, very rare to find, and we would learn a lot from it, and we shouldn't be losing these opportunities. So what should we do? Can we install, let's say, inexpensive seismometers in those locations? What should we do?
Yeah, there's a lot that will happen. There are a lot of donations that are going to happen. I think the Global Seismic Network is likely to expand, and that has a business model that will allow it to keep going. I think the Tongans are interested now. With this event, they'll need to figure out something that works for their purposes if they have to do some of the maintenance. So, it's a complicated story. I would say that even though part of the story was lost, there's a lot that we've learned, a lot that we can access through satellites and other techniques. And we'll move on and try to do it better next time.
Also, bear in mind, if this little eruption way over there caused $10 billion of damage in California, so this shouldn't be just Tongans kind of come up with the money and try to figure out what they can do. We can help too, because this actually impacts us, and that would be a good investment in our part if California, installs some stations there to gain some time. My
And-
last question to Rick is, how much time do we have when there's an eruption or earthquake like this happens anywhere in the world? How much warning time in terms of tsunami do we get in California?
Well, our very north coast has the Cascadia subduction zone right offshore. So north of Cape Mendocino, it could be a matter of minutes. And the earthquake is basically the notification that the tsunami may be generated. Other than that, we have sources that are anywhere from 4 to 13 hours away. Basically, that tsunami travels the speed of a jet plane. So if you're flying a plane from Alaska to California, it takes 4 to 5 hours, and that's about how long it takes for the tsunami to get here. And that time is really important. So the more information we get from the warning centers, the faster we get it out to the local agencies, the better they'll be able to respond. And that's really our the takeaway here is trying to improve that in the future.
So what you have said is very important take home for the general public. If you are feeling an earthquake, don't go to the beach. Go to the higher ground. You never know whether or not there will be tsunami following. Because, even if, let's say, San Andreas or Hayward Fault ruptured, even though strike slip faults won't necessarily generate uplift, especially when they're inland, but there could be, underwater landslide could generate these tsunamis. So we got to make sure that we don't be watching the ocean. Well, on behalf of our Northern California chapter, I would like to thank you both. This was such an informative and impactful meeting. And we tried a new format. We are broadcasting this live on YouTube. So we hope to reach to a much larger audience to increase our impact. Thank you so much.
Thank you.
Thanks.
And just
All
back
right. Perfect.
Oh, well,
Are we off the live now?
for anyone who's still with us, thank you again. You can learn more about EERI at our website and join EERI there. By becoming a member, you help support events like this one. And to find out about upcoming webinars, not just ones hosted by the chapter, you can also check out our Pulse newsletter on the website at that address. Finally, we'd like to thank both EERI's members and FEMA and the Department of Homeland Security for supporting events like these. Thank you.